Now that we know that steric hindrance can favor elimination reaction and that we need an alpha hydrogen and that we can get a Zaitsev and Hofmann product, we need one more thing, and it's the fact that hydrogens need to be anti-coplanar to the leaving group. Now, in this situation, for example, over here, we have a tertiary carbon. It's connected to 3 carbons, these 2, and then the back one. And so we're not going to get an SN2 reaction if we react it with our methoxide ion over here. So it's going to be an elimination reaction because methoxide ion is a strong base. Now, where is our anti-coplanar hydrogen? Well, on the back carbon over here, we have a hydrogen that's perfectly anti to our front bromine right here. And because it's anti, we can do an elimination reaction where our oxygen, which is going to act like our base with its lone pair, is going to go to this hydrogen, attack it, and then the lone pair, or not the lone pair, but rather the electrons connected to this hydrogen are going to move and form a bond with this front carbon over here, and bromine is going to take a lone pair with it and leave. And so what we end up having for our product is on the front carbon we have our methyl on the left, our ethyl on the right, a double bond with the back carbon, and then on the left we have an ethyl, and then on the right we have a methyl. And so that's our final product, and that's all there is to it. Now, for this next example, not only do we need the hydrogen to be anti to the bromine, but we also need the bromine to be axial. And so let's draw the conformation for the cyclohexane where the bromine is going to be up and axial. And so I'm going to draw the conformation like this. I'm going to put the bromine right here. So the bromine is going to be up and axial. Now on the next carbon over here, we're going to have our methyl going down. Now we need our hydrogen to be anti to our bromine. It also has to be axial. So not only does the hydrogen have to be diaxial to the bromine, but it also has to be anti. So it's pointing down instead of up. Or if the bromine is pointing up, the hydrogen has to be pointing down, just in the opposite direction. So let's label our alpha hydrogen. So we have one alpha hydrogen over here. So we have one that's pointing down and one that's equatorial pointing up. And then over here, we have another one that's pointing up as well, and it's equatorial. So which one of these is not only axial, but pointing down? Well, the only option over here is this hydrogen right here. So our butoxide over here is going to act like a base because it can only act like a base. It's too hindered to act like a nucleophile. Is going to attack this hydrogen right here. Our bond is going to basically go to this carbon and form a pi bond, and bromine is going to take a lone pair with it and leave. And so our final product will look like this. It'll be our cyclohexane, and we'll have our methyl group still over here, and our double bond will be right here. It won't be with our methyl group. Now, what's a little trick to tell us if this is going to work? Say, for example, we had this instead. We have our bromine up over here, and we have our methyl, rather than going down in the previous example, is also going up. Now that this methyl is going up, we can get up to 2 products. We can get the product that has a double bond right here and the methyl is still going up, or it can have the product where double bond is with the methyl, and now the methyl group is no longer going up or down, but rather on the same plane. And so this will be our Zaitsev product, and this will be our Hofmann product. And so we just have to use a strong base in order to do this. Now just know if you have a hindered base, you'll get your Hofmann product as the major, like this. Or if you use an unhindered base, you'll end up getting your Zaitsev product like this.